Alright, the purpose of this video is to hopefully clarify some concerns that students had about carrying out the calculations at the end of our activation energy lab. Okay, and probably one of the first things that we should do here is to clarify what activation energy actually is. Okay, so if I were to consider a reaction where I have some reactant A being converted to some reactant B. Okay, and if I looked at the energy of the reactants in the products, okay, I would notice that they have different energies. Now, in this particular case, I've decided to show the reactants as being higher in energy than the products. So this is an exothermic reaction, but this works just as well for an endothermic reaction also. Now, the way that I've drawn this kind of implies that our reactants just kind of magically convert into products. Okay, but that's not really what happens. What really happens is that the reaction actually has to follow a pathway, a mechanism, where the reactants are going to be raised up in energy and they're going to be converted into the product. Okay, and that looks something like this. Okay, so we need to increase the energy of the reactants, kind of physically have them change shape until we get to our products that we're looking for. Now, the amount of energy that has to be attained to do that is called our activation energy, which we symbolize as E sub A. Okay, and that state that we are trying to achieve, that barrier we're trying to overcome, is called the activated complex. Sometimes you'll see this also referred to as the transition state, and both are acceptable. Okay, so that activated complex is the energy, or is the structure that needs to be achieved in order for our reactants to ultimately be converted to products. Okay, and the higher that activation energy is, the slower the reaction is going to be. Okay, so as the activation energy increases, okay, we see a slower reaction rate. Okay, now something else that we notice is that there's a connection between the rate of a reaction and the temperature of the reaction. And when you think about it, that kind of makes sense, because if we do something that's going to increase the temperature of the reaction, we're going to be increasing the energy of the reactants. Okay, remember, temperature and kinetic energy were kind of intrinsically linked. So by raising the temperature, we're raising the kinetic energy of the reactants, which is going to decrease the amount of energy that they need to take in to get to that activated complex, to overcome the activation energy. So generally speaking, we see that at higher temperatures, we see higher rates. Okay? And that's what we're going to be evaluating here in this experiment. So if you're thinking back to your readings, we had this thing called the Arrhenius equation. And the Arrhenius equation kind of brought all these variables together, in that we could look at the rate constant in terms of a couple of different values here. A being a constant that is dependent upon what the reaction is, okay, times E raised to the power of the negative of the activation energy over RT. Okay, so you can see here we have A, which is a constant, okay, E, which is a constant. We have the activation energy, which would be constant for a particular reaction, and then the gas constant and temperature. Okay, so our two variables here in a given reaction are the rate constant and the temperature. So for a given reaction, everything else stays constant. Okay, and if we were to plot these, where we look at K on the y-axis and temperature on the x-axis, we would get a plot that looks something like this. Okay, exponential, which is what we would expect given the equation that we saw. But in its form that I have drawn there, it's not a terribly useful equation. However, we can linearize this equation by taking the natural log of both sides. And what we get here is the natural log of k, being equal to the negative of the activation energy over R times 1 over T, the absolute temperature in Kelvin, not in degrees Celsius, plus the natural log of A. If we look at this closely, we can see here that this is in a linear form. Where you can see that the natural log of A is our y-intercept. Our slope is going to be equal to the negative activation energy divided by the gas constant. And then if we create a plot of natural log on our y-axis, and 1 over T on our x-axis, then we could actually use that data to figure out what the activation energy is for a reaction. And that's what happens here. So what we're going to do is we're going to be using experimental data for the rate constant and for temperature. So what I gave you to use for the experiment were a set of rate constants with corresponding temperatures. So we have some temperature 1, 2, and 3. And what you would have done in the laboratory is you would have carried out this particular reaction at 3 different temperatures, and you would have measured the rate constant for each one of those. So we'd have these 3 rate constants corresponding to the 3 temperatures. Now, in order for us to get into this linearized form, we're going to have to take the natural log of our rate constant. So that means for each one of these data points, we're going to measure or calculate the natural log of each one of those rate constants. And then we're going to take those temperature values and we're going to take the inverse of them, again remembering to be in Kelvin, not in degrees Celsius. So it'll be 1 over T1, 1 over T2, and 1 over T3. And what we can do then is we can plot these values of natural log of the rate constant against the inverse of the temperature. And we'll have a plot. And that plot will have the natural log of K on the y-axis, and it'll have the inverse of temperature on the x-axis. And what we'll find is that the plot that is created here will look like this. In other words, if we plot the data points and put them into Excel, we'll get a trend line that goes right through here, and we should be able to figure out the equation for that trend line from Excel. And again, we can look at the value for B, and that will be equal to the natural log of A, which in this experiment we're not really doing much with. But we can take that value for slope, and that value for the slope is going to be equal to the negative of the activation energy over R. Now that's very useful. Okay, so slope is a value that we can pull from the equation that we get from Excel, and that's going to be equal to the negative activation energy, okay, over R, which means that we can take the gas constant, actually the negative of the gas constant, and multiply that by the slope of the equation, and that'll give us our activation energy for the reaction. So that is how we calculate the activation energy from the experimental data that I gave you. Okay, now for questions 4 and 5, we're going to be still utilizing the Arrhenius equation, except we're going to be utilizing a different form, which allows us to look at two sets of conditions. Okay, you might remember this. It said that the natural log of K1 over K2 was going to be equal to the activation energy of the reaction divided by the gas constant times T1 minus T2 over T1 times T2. Okay? So what the question 4 is asking us to do is to verify this old adage that we had in chemistry that the rate doubles for every 10-degree increase in temperature. Okay, now, how do we do this with our data? Well, if you look at the reaction data, what you're going to want to do is you're going to find two trials that were separated by about 10 degrees. And if I were you, I would choose trial 1 and trial 3. Okay? And what I would do is I would plug in the activation energy that we calculated from question number 3. Okay, and we plug in our gas constant, which is our 8.3145 joules per mole Kelvin. Now, a word of warning here, make sure that if you keep your gas constant in units of joules, that you make sure your activation energy is in units of joules as well, or make sure they're both in kilojoules. Either way, make sure that they're in the same units. Okay? Then you're going to say, take your trial 1 data and put that temperature in here. Okay, and then trial 2 data. And plug it in there, and then of course at the bottom as well. Okay, so I think one of them is 20.8 and the other one's 10.5. All right. And again, just plug that data in, and what you're going to get is some value here, where you'll be able to take e to the power of K1, K2, and set that equal to e to the power of whatever this big chunk is equal to. Okay, and you're going to get, as your answer, K1 over K2 equal to whatever e to that power of that big chunk was. Okay, now, if T1 was 10 degrees lower than T2, that means that the ratio of K1 to K2 should be 1/2. Okay, or somewhere about that value. Okay, so if you can get to the point where you calculate K1 over K2 and that equals roughly 1/2, and it doesn't have to be perfectly 1/2, that would tell us that this old adage is true. In reality, it's not going to be exactly true. It's just a rule of thumb. But it works for most reactions. Okay, so that's what you're going to do for question number 4. In question number 5, it's the exact same kind of idea. Okay, if we look at that equation that we started off with, okay, where we have the natural log of K1 over K2 equal to the activation energy over the R times T1 minus T2 over T1 times T2. Okay, what we're being asked is to look at a set of conditions and to figure out what the rate constant is going to be at another set of conditions. Okay, so what you could do is use your activation energy that you pulled from your data, that you calculated from the slope of the line and everything. Okay, plug in the rate constant for one of those sets of data. So if I were you, just pick trial 1, right? So plug in K1 for trial 1. Okay, that means you're going to use the temperature for trial 1 as your T1. So you plug that in for both of these. And what we're trying to figure out is what is the rate constant going to be at 40 degrees Celsius. Okay, and that means we're going to plug in, well, 40 plus 273 is 303 Kelvin in for both of these. And ultimately, you're going to calculate K2. Okay, K2 is what the rate constant would be at 40 degrees. Okay. Now, in the actual question, it says you should try to use the one that was at room temperature. So that just means that you can use your trial 3 data or trial 4 data for K1 for your activation. Well, you already have your activation energy and your T1. Okay, and that should get you to the answer that you need for question number 5. Okay, now I know this video was put together kind of haphazardly. I know the audio quality is not fantastic, but if you have further questions, please let me know, and I'll make another video, or I'll hop on to Google Meet or whatever we need to do.